Different hearts, different dreams. Injective souls ignite the beams. No dream alone, no path ignored. Surjective wills knock every door. More hearts to thrive, or more dreams to grow. Two mighty sets now march toward battle. The wings of cardinality raise us high to the heaven of infinity, beyond the sky.
Previously, we introduced the concept of equinumerosity. Recall that two sets A and B are said to have the same cardinality if there's a bijection from A to B. In today's section, we'll walk through a few classic examples. In each case, we'll define the function explicitly and prove its bijectivity. Let's start by showing that the set of natural numbers n and the set of integers z are equinumerous. To see this, we define a function f from n to z as follows. Given a natural number n, if n is even, we send it to n divided by 2. If n is odd, we send it to negative n plus 1 divided by 2. In particular, observe that fn is non-negative when n is even, and negative when n is odd. Now let's check that it's injective. Suppose that fn1 equals fn2 for some natural numbers n1 and n2. If the common function value is non-negative, then both n1 and n2 must be even, and by the definition of the function in this case, we get the following equation. If this common function value is negative, then both n1 and n2 must be odd, and by the definition of the function in this case, we have instead the other equation. In either case, solving the resulted equation gives n1 equals n2. We conclude that f is injective. Now for surjectivity, pick any integer y. If y is non-negative, then pick n equal to 2y, which is an even natural number, and following the definition of f in this case, n is mapped to y. If y is negative, then pick n equal to minus 2y minus 1. Since y is a negative integer, y is less than or equal to negative 1. It follows that minus 2y minus 1 is greater than or equal to 1, hence indeed an odd natural number. 1 verifies that f of n equals y accordingly. We conclude that f is surjective. Now, since f is both injective and surjective, it is bijective, which proves that the cardinality of n and the cardinality of z are the same. You might find it slightly anti-intuitive, as n is strictly contained in z. Yet remember that an infinite set can be bijectively mapped to some of its proper subset, a key property that distinguishes an infinite set from a finite set, which we have already mentioned in the previous section. Next, let's study the cardinality of open intervals. Take any two real numbers, a and b, with a less than b. We want to show that the open interval ab has the same cardinality as the open interval 0, 1. The function we use is this, fx equals x minus a divided by b minus a. This function can be seen as the composition of two functions. First, it shifts the interval ab to 0b minus a, so it starts at 0. Next, notice that the length of the interval is b minus a. We thus rescale it so that its length becomes 1. To prove injectivity, suppose fx1 equals fx2. Then we have the equation x1 minus a over b minus a equals x2 minus a over b minus a. It follows that x1 must equal x2. To prove surjectivity, take any number y between 0 and 1. Define x to be y times b minus a plus a. That x lies inside ab, and plugging it back into f gives exactly y. So again, we have a bijection. These two intervals are equinumerous. Now here's a slightly more abstract one. Let S be any non-empty set. We look at the set of functions from S to the set 0, 1, which is denoted as 0, 1 to the power S. We want to show this set has the same cardinality as the power set of S. As usual, we first construct a function and show its bijectivity. Keep in mind that each element in the domain is a function of its own right, while each element in the codomain is a set. For any function f from S to 0, 1, we define a map G that sends this function to the preimage of the singleton 1 under F, which is a subset of S, and thus an element in the power set of S. For injectivity, suppose two functions f1 and f2 are such that gf1 equals gf2. This means the preimage of the singleton 1 under f1 coincide with that under f2. In other words, the two functions achieves the value 1 on the same set. Since both functions can achieve either 1 or 0 on each point of S, those points in S which are not sent to 1 must be sent to 0. It turns out that the two functions achieve 0 on the same set as well. As a result, f1 and f2 always achieve the same value, so the two functions are equal. For surjectivity, given any subset T of S, define a function ft that outputs 1 for elements in T and 0 otherwise. The preimage of the singleton 1 is exactly T. That means ft is mapped to T under G, and the map is thus surjective. We conclude that the function G is bijective, therefore the equinumerosity of the two sets. You have now seen how to justify the equinumerosity of two sets by constructing a bijection between them. In general, such constructions might not always be trivial. We will explain in the next few sections convenient properties and alternative tools to facilitate such comparisons.
신라 텐세